Good morning, afternoon, or evening. How you all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to be talking about congruent angles associated with parallel lines. Now we've seen quite a bit of this today already, and today we're going to hopefully just go ahead and solidify the knowledge. And we're going to first start with the parallel postulate. And the parallel postulate states that through a point not on a line, there is exactly one line parallel to that given line. So if you have this point right here, this red point that you see, and you see this line below it, okay? If we draw a line through that point, there is another line that is parallel to that, right here. Okay? So if I have a point here, there is definitely a line that is parallel to that point. Okay? Now that's very important. Remember that. Now, although this idea may seem reasonable, believe it or not, mathematicians argued for centuries over the truth of the parallel postulate. But since we study Euclidean geometry, it's called Euclidean because Euclid was a Greek mathematician, and that's what we base geometry on. We will assume that parallel postulate holds true. Okay, so the alternate interior angle theorem. The alternate interior angle theorem states that if two lines are parallel, as seen below, okay, if two parallel lines are cut by a transversal, each pair of alternate interior angles are congruent. So what that means is if you have parallel lines, then the alternate interior angles are congruent. Okay, we've seen this already before, but like I said, I just wanted to solidify things. The transversal theorem. The transversal theorem states if two parallel lines are cut by a transversal, then any pair of the angles formed are either congruent or supplementary. So the alternate interior, alternate exterior, corresponding, same side, all of that is proven by this transversal theorem. If two parallel lines are cut by a transversal, then any pair of the angles formed are either congruent or supplementary. The proof of this theorem may be developed algebraically by using vertical angles, or geometrically by using corresponding angles and alternate interior angles, and also, to be honest with you, same side interior angles. Let's show you what I mean. If I have these two parallel lines, okay, and they're cut by this red transversal here, and I have this angle x, well, by vertical angles, that angle is also x degrees, okay? By using the supplementary theorem, we know that the angle to the right of the original x is 180 minus x, because both of these angles are supplementary. Using same side interior angles, if this guy here is x, then that means that this is 180 minus x. Or, if you remember, the F theorem, which is the corresponding, top side is congruent to top side. Okay? Using corresponding angles once again, if I have this angle x, then underbelly is congruent to underbelly. So we have this x. Or we could state, because of supplementary angles, you have 180 minus x and x. By using vertical angles, this guy here is also x, or we could see that if this is x using corresponding angles, this has to be x. Okay? Using vertical angles or supplementary angles, if we have this is 180 minus x, then this has to be 180 minus x as well. Another way to look at this, if we use the z method, this guy and this guy are alternate interior angles. And last but not least, if this guy here is 180 minus x, using corresponding angles, this guy here has to be 180 minus x. So again, the transversal theorem is very powerful. If I have two parallel lines and they're cut by a transversal, then that means that all of the angle pairs are either congruent or supplementary, period. All right, let's continue. Alternate exterior angle theorem. The alternate exterior angle theorem states that if two parallel lines are cut by a transversal, each pair of the alternate exterior angles are congruent. I want you to note, though, that alternate exterior angles are always vertical to the alternate interior angles. So basically what we're saying, if you have parallel lines, then alternate exterior angles are congruent. So that means that angle 1 will be congruent to angle 2. But let's check out the note here, okay? This angle 2 is vertical to this angle, so this would be angle 2. And this angle 1 is vertical to this angle 1. So if I do the Z method, alternate interior angles, the alternate interior angles are going to be congruent to the alternate exterior angles because of vertical angles. Corresponding angle theorem. Corresponding angle theorem states that if two parallel lines are cut by a transversal, each pair of corresponding angles are congruent. So if I have parallel lines, corresponding angles are congruent. So since these two lines are parallel, angle 1 will be congruent to angle 2. Remember, this is the F. Okay? You have top side to top side and underbelly to underbelly. That's corresponding angles. Same side interior angle theorem. Same side interior angle theorem states that if two parallel lines are cut by a transversal, each pair of interior angles on the same side of the transversals are supplementary. So therefore, if A is parallel to B, then angle 1 and angle 2 are supplementary. So that means that angle 1 plus angle 2 will equal 180 degrees. That is the same side interior angle theorem. Related to that is the exterior angle theorem. The exterior angle theorem states that if two parallel lines are cut by a transversal, each pair of exterior angles on the same side of the transversal are supplementary. Please be careful, this is not corresponding. If you notice, this is top side, this is underbelly. So they're not congruent. What this is stating is that if two parallel lines are present, okay, and they're cut by a transversal, then these exterior angles, 1 and 2, top side and underbelly, will equal 180. They're supplementary. So in this case, the top side and the underbelly, angle 1 plus angle 2, equal 180 degrees. Perpendicular theorem. The perpendicular theorem states that in a plane, if a line is perpendicular to one of two parallel lines, it is perpendicular to the other. So what this is saying is if I have line A parallel to line B, and I tell you that line C is perpendicular to A, then it has to be perpendicular to B. If A and B are parallel, then A and B are perpendicular to C, as long as C is perpendicular to one of these. Transitive property of parallel lines. Transitive property of parallel lines states the following. If two lines are parallel to a third line, they are parallel to each other. So if I tell you that A is parallel to B, and B is parallel to C, then that means A is parallel to C, and therefore A, B, and C are all parallel to each other. So if A is parallel to B and B is parallel to C, then that means A is parallel to C, and that means that all three are parallel to each other. Okay? So let's get to it. If line C is parallel to line D, find angle 1. Okay. Think about the Z method for alternate interior. Think about the F method for corresponding. And think about the C method or U method for same side interior. Always think of those. Those are going to help you. In this case, I have a backwards Z. So that means this angle is congruent to this angle because of alternate interior angles. So therefore, 3x plus 5 is equal to 2x plus 10. Let's solve for x. All right, hopefully you can see what I'm doing here, simple algebra. So I've derived that x is equal to 5. If x is equal to 5, let's plug it in. 3 times 5 plus 5, that's 15 plus 5 is 20. Now because of vertical angles, these guys are vertical, okay? Since this is 20, then that means angle 1 is also 20 degrees. Nice and easy. Use the Z, the F, and the U to help you, okay? Number 2, let's do your favorite, a proof. I'm saying that FA is parallel to DE. FA is also congruent to DE, and AB is congruent to CD. I want to prove that angle F is congruent to angle E. All right, let's see what we got here. Number 1, FA is parallel to DE. So FA is parallel to DE. That is given. Number 2, angle A in that case will be congruent to angle D. Now you may say, how did you come up with that? Use the Z method. See that Z in green? So that means alternate interior angles are congruent. So if you have parallel lines, then alternate interior angles are congruent. Okay? Or you could say the alternate interior angle theorem. FA is congruent to DE. So FA is congruent to DE. That is a given. They also tell you that AB is congruent to CD. So AB here is congruent to CD here. That's also given. Now look at segment AD, okay? And look at AB and CD and BC. Hopefully you can see that AC will be congruent to BD. What am I saying? AC is congruent to BD. Why? Because of the addition property. Now some of you are going to say, wait a second, you skipped a step. Shouldn't you have said that BC is congruent to BC because of reflexive? Yes, you could have, and I'm not going to mark you wrong if you did put that, but it is pretty much assumed here at this point. So since AB is congruent to CD, and you're adding segment BC to both, then AC must be congruent to BD because of the addition property. Well, now look at what we have. We have this triangle FAC, and we have this triangle DEB congruent to each other. Why? Because of side, angle, side. Here's my side, here's my angle, here's my side, Here's my side, here's my angle, and here's my other side. And then we can easily state that angle F is congruent to angle E, the proof, because of CP/CTC. Pretty simple. But it all started with this alternate interior angle theorem. So please look for the Z's, the F's, and the U's. It's going to help you out a lot. Okay, example 3. Given line G is parallel to line H, I want to prove that angle 1 is supplementary to angle 2. Well, how are we going to prove that? Very easily. Let's check it out. Number 1. Sorry, it's not angle G, it's line G is parallel to line H. My bad. I apologize. G is parallel to H. That's given. Okay, from here, let's think about this. What shape can I use here? Do you see the U here, or the C, however you want to see it? Think about that. One thing we can state for sure is that angle 2 is supplementary to angle 3. That's definition of supplementary angles. Angle 1 is congruent to angle 3, and actually that U really doesn't play a part here. What would have played a part here more is the Z. I look at the Z, aren't alternate exterior angles congruent? You could have used the U, but it would have been a much longer proof, so I apologize. If you use that Z, though, angle 1 is congruent to angle 3 because of the alternate exterior angle theorem. If you have parallel lines, alternate exterior angles are congruent. And then if angle 2 is supplementary to 3 and angle 1 is congruent to angle 3, then angle 1 is supplementary to angle 2 because of substitution. Now, you may say, whoa, why isn't it transitive? Remember, when we're talking about values, it's substitution. And when we're talking about supplements, those are values. Example 5. Figure ABCD is given with AD being parallel to BC, AB is congruent to DC, and AB is not parallel to DC. I want to prove that angle B is congruent to angle C. All right, let's check out this proof. It's a bit of a monster. So let's go through it nice and slowly. Number 1, you have figure ABCD with AD being parallel to BC. So AD is parallel to BC. That is given. Number 2, AB is not parallel to DC. Just know that. AB is not parallel to DC. That's also given. Number 3, you can draw DE being parallel to AB. Okay? Let's think about this. You have AB here. All right? But DE, I can draw DE because of auxiliary lines. And remember the parallel postulate theorem. If you have a line, I can draw another line parallel to that line because it's going through a given point. Where's that point, Mr. Morrill? Remember that when we draw auxiliary lines, lines are made up of infinite number of points. So I can draw DE being parallel to AB because of the parallel postulate. You can also now draw AE. And if I draw AE, I draw that because of auxiliary lines. Now I can say that DAE is congruent to BEA. So DAE, which is this guy right here, is congruent to BEA, which is DA. Oh, I'm sorry, I went a little too far there. DAE is congruent to BEA. Why? Because of the Z alternate interior angle theorem. From there I can say that BAE is congruent to DEA. BAE is congruent to DEA. Remember that we had stated that BA is parallel to DE. So I can once again use my alternate interior angle theorem. Now I can state that AE is congruent to AE because of reflexive property. Now this should be jumping out on you. Triangle AEB is now congruent to triangle EAD because of angle, side, angle. We have the angle, we have the side, and we have the angle. Angle, side, angle. Now I can state that AB is congruent to DE. AB is congruent to DE because of CPCTC. Then from there we can state that AB is congruent to DC because it's given. So that means this guy's congruent, right? Then from there I can state that DE is congruent to DC because of the transitive property. Why transitive? Well, if AB is congruent to DE and DE is congruent to DC, then that means that AB is also congruent to DC because of the transitive property. From there, I can state that angle DEC is congruent to angle C because of if sides, then angles. Then I can state that angle B is congruent to angle DEC. Now think about this one. Here, we're going to use the F method. Here's my F, or in other words, corresponding. Since we know that BC is parallel to AD, then we know that angle B is also congruent to angle DEC because of corresponding angle theorem. And then from there, I can state that angle B is congruent to angle C because of transitive property. Why? Well, we had already stated that angle C was congruent to DEC. Then we stated that angle B here is also congruent to DEC because of corresponding. So then we can state that angle B is congruent to angle C because of transitive property. And that's it. Heavy proof. But if you take your time, watch this video repeatedly, really focus, I know that you can do it. Thank you very much. Have a wonderful day, and I hope you learned a lot. Take care. Bye-bye.